Hello, everyone. Thank you for joining us today. My name is Julie Rupert. I'm the marketing manager for our high school science line, and we are so excited to have you join us today for our at-home learning webinar, Wave, Dynamic, Dangerous, or Delicious, with Chuck McMillan. Chuck is a national science specialist. As a former science teacher, his enthusiasm for hands-on learning and engaging conversations has allowed him to take his success in the classroom on the road to K-12 science educators. Chuck is featured in educational videos for our best-selling science titles and also conducts trainings, presentations, and workshops across the country. Now, before we get started, I have a few housekeeping items for you. All of your lines have been muted. If you have any questions, just ask them in the questions box on the side of your screen. I will take care of answering those for you during the presentation. If you have any questions for Chuck, I can read those out loud for you at the end. Chuck is also going to ask those of you in the audience a few questions throughout the session. When he does that, please type your answers in the question box. But don't worry, nobody can see your answers but me, so don't be afraid to guess if you don't know it. If you've enjoyed this webinar, or if you have others that you'd like to share it with, we are going to post a recording of the webinar on our blog by the end of the week. I have shared the blog link in the chat box on the side of your screen. If you have trouble seeing that, just send me a quick question and I'll send it to you individually. We hope to have all of these recordings posted by the end of the week. And if you'd like to sign up for our last physics webinar tomorrow, you can do so on the blog as well, or follow us on social media on Twitter, Facebook, and LinkedIn. With all that out of the way, I'm going to go ahead and turn it over to Chuck. Thank you.
Thank you, Julie, and welcome everybody. I'm really happy to be here. I'm happy to finally have this together. And, Julie asked me a few weeks ago if I would do a presentation. Now, when I was teaching, I used to do 5 preps a day. I would teach, maybe a chemistry, a physics, a biology, an earth science, whatever. And I want to say that I think I put more time into this presentation than I would put into a whole week's worth of lessons back when I was teaching. So I think it was the added stress of being live online. But anyway, welcome to Waves, Dynamic, Dangerous, or Delicious. Now I'm going to there we go. Again, this is me, Chuck McMillan, and I agreed to do this presentation today, but I thought it'd be really difficult to do an online presentation because when I was teaching, I wasn't one who liked to talk a lot. In fact, one day, one of my co-teachers came down to me and she said, we were talking in social studies today. She was teaching 8th grade social studies, and at the time I was teaching 7th grade science, and she said, we had a discussion going today in social studies, and we were talking about something that had a scientific relation to it. And so I said to the class, well, what did Mr. McMillan teach you last year? And she said, one of the kids put up his hand. His name was Zolt Top, and I'll always remember his name for this very reason. It was probably the nicest thing anybody ever said about me as a teacher. And he said, Mr. McMillan didn't teach us very much. And she paused for a second, then she said, but then he went on to say, but we learned a lot. And that's because I used to love doing experiments and doing activities and not so much standing up and talking. So I was trying to find out ways that I could fill in a full hour or, between half an hour and an hour in a lesson today. And I really want you to, instead of just listening to me, I want you to really experience physics today. And as luck would have it, Experience Physics is actually the name of a brand new program that we've put out that's going to be coming your way soon. And as a matter of fact, when Julie asked me to do the presentation, I said, well, we have a new physics book, don't we? Yes. And so she sent me a copy of the one sample chapter that we have, and it's arranged in a series of storylines, and one storyline happened to be on waves and electromagnetic radiation. And that's actually divided up into 3 different investigations. One is on just waves, electromagnetic radiation is another one, and information instrumentation is the 3rd investigation. But we only have one of those investigations ready to go, and it's a sample chapter that I could work from on waves. Now, here's the thing. The whole program has been built around investigative phenomena. And I saw that we have a few people in the group that are attending today. I'm not sure if you're teachers or whether you're students or maybe, teachers who are students themselves. But if you're not familiar with this term phenomena, it's really important in next generation science, because the reason for teaching science is not just to get a credit, not just so that students can learn something, an academic pursuit that has no connection to them, but it's to use science to understand things in the world around them. And we call these things that happen in the world around you phenomena. And so what we try to do is connect learning to phenomena to make it more meaningful to students. And again, if you're a student out there, we're taking a look at a certain investigative phenomenon today, and I'm going to be delving deeper into this phenomenon. Now, my objectives for today are three things. Number one, I want to provide some insight into the behavior of waves for you so that you can walk away from here and know maybe a little bit more about waves. Second thing is I want to suggest and link you to some tools for self-study on waves. We've got some great partnerships with this new program, and I'm going to send you to some places where you can find some really cool stuff to do. And the third thing is, of course, to kill an hour or so of quarantine time, and so that your day doesn't come out to be a complete waste, and it'll give me something to do for an hour as well and make my day pass a little bit faster. So let's get back to that investigative phenomenon. And to understand it, I want to show you where I live. So I'm on Google Earth right now, and I'm zooming into Port Huron, Michigan, which is right at the southern tip of Lake Huron. And let me back away and kind of orient you here and show you what the Great Lakes look like. So here are the Great Lakes, and if you're not familiar with the Great Lakes, if you're not from the area or have never really heard too much about them, this is Lake Superior, Lake Michigan, Lake Huron, Lake Erie, Lake Ontario. The water flows from the upper left down through to the lower right out of Lake Ontario into the St. Lawrence River. And there's a lot of water that passes through there. In fact, a major portion of the fresh water on Earth is found here. And it's really cool living in this area. Like, I love it. I grew up on Lake Ontario. I lived in Nova Scotia for many years and taught down there. But now I live right at the southern tip of Lake Huron. I'm back on the Great Lakes, and I love it because it's really beautiful here. This was sunrise this morning. I got up and I walked over to the beach and I took a picture just so I could put it in this presentation. But there's some things that are happening right now in the Great Lakes that are really kind of weird, and I want to investigate them with you and see if you can figure out something about them and figure out the phenomenon. So what I did was I put together a phenomenon video for you, first of all. I went in online and looked up this phenomenon to see what I could find and put together a video. Now, here, Julie had said we're going to give you some questions throughout the presentation today. And one of the questions is, what do you see in this video? What is it that strikes you in here? A second thing is, what questions would you like to have answered about the phenomenon? So I want you to start thinking about, what am I seeing? What questions would I like to have answered? Now, this phenomenon video number one, I put the video in. Let's see if I can get it to run right here. So let me try it this way, and here we go. Now, there's no sound, so I'll be quiet and just let you view this. Okay, now the video is a little bit long, but I'm going to ask you to just take about a minute or so and jot down some things in the chat for me. And Julie, as they come in, if you would be so good as to read them, I'd like to hear what people saw in the video and what questions they have about the video.
Okay. For those of you in attendance, you can put your questions or your observations, just type them in the question box, and then I'll go ahead and read those out loud for you. All right. Someone in the audience said that they saw waves, destruction, energy, major energy, wind erosion. Somebody wants to know what is the source of the waves being so big. I noticed we're looking at waves eroding the land. What is causing some high energy waves? I saw waves on Lake Michigan and erosion. Why is erosion increasing? Motion and energy. In the windsurfer clip, why was the windsurfer traveling sideways when the waves traveled forward? Well, that's a good one. Deep water waves, water level rising. How high are the highest waves on the Great Lakes? Got a lot of questions here.
Some awesome questions, yes, and you know what? I hope we get a chance to answer a lot of those today as we go through. So I wanted to set up that phenomenon video and to take a look at what you saw and the questions that you had, because that's the best starting place anytime that we're doing a physics lesson, because it makes the learning more meaningful to you. So what I've done is I've put together a little presentation. I'm going to take you through some more videos, some experiences, and we're going to start off with what exactly is a wave. Well, as you know, a wave is a phenomenon that moves energy from one place to another. Now, if I wanted to knock something over, I could, take a ball and throw at it. I could blow it over. I could shake a table and that it was sitting on and make it fall over that way. Basically, what I'm doing is I'm transferring energy. Well, waves transfer energy as well from one place to another, but it's the energy that moves and not the particle. If I throw a ball at something, what I'm doing is I'm moving a particle, whereas with a wave, the particle more or less stays in the same place. It moves about that same place, but the energy is transferred through the wave. Now, there are a couple of different types of waves, and those include mechanical waves and electromagnetic waves. And if you were paying attention earlier, you saw that the next experience that's in this, the next investigation in this program would be electromagnetic waves. So what's the difference? Well, mechanical waves, they transmit energy through a medium. They can't move through a vacuum. So they can't work in outer space, for example. Electromagnetic waves, on the other hand, don't require any kind of a medium. They can move through a vacuum. Now, the electromagnetic waves are pretty cool, and they're great to study. Here they're being shown with the electromagnetic spectrum. And starting on the left, we have shortwave, very intense, very powerful waves. Over on the right, longer, less powerful waves, less intense waves. And this whole range of wavelengths have created for us a number of different things that we find in our lives that we use, from gamma radiation over on the left to X-rays up above that, ultraviolet light, the visible light spectrum, infrared radiation, radar, which works not only for tracking planes and boats and things like that, but also the Doppler radar that's used for determining weather and predicting weather. Your TV set runs on waves, electromagnetic waves, as does your radio, or maybe I should say your grandmother's radio. But the thing is this: we're not going to be studying electromagnetic waves today, but one of those pictures does have a clue to some of the questions that you were asking a little bit earlier, and we'll come back and see if we can determine which one that was a little bit later. Now, we're going to take a look today instead at mechanical waves, and there are two different kinds of mechanical waves. Now, there are two different types of people in this world, those who divide things into two types and those who don't. I happen to be one of the ones who does, and so we've got transverse waves and longitudinal waves. And of course, if you've studied them at all before, if you played with a slinky before, you may know some of the characteristics. In fact, if you're a high school student, you're probably looking at this saying, this is, I know this from middle school or whatever, and that's just fine. But let's take a look and dive a little deeper into the different types of waves and see what we can find out. Now, transverse wave, first of all, one of the features of the transverse wave is the wave movement, the direction of movement. And so the direction of movement goes, in this case, from left to right. It goes on a certain plane. The direction of movement of the particles, though, is perpendicular to that plane, it's up and down. So in other words, the wave movement is perpendicular, the particle movement is perpendicular to the wave movement in transverse waves. Longitudinal waves, on the other hand, the wave movement goes in the same direction, and the particle movement is parallel in this case, and the particles that are creating or transferring the energy in the wave move in the same direction as the wave movement. Now, again, longitudinal waves are pretty cool. One of my favorite ways to transmit longitudinal waves is through music, and I put together this little video to describe the differences between transverse and longitudinal waves. Now, I don't know if you've ever seen an image like this on the left where you can actually put your cell phone down inside of a guitar and put the camera on, the video camera, and it will pick up the vibrations, the transverse waves in the strings. And then I put that together a little video to look at the longitudinal waves just because I kind of like it. Now, I'm not sure if you'll be able to hear this. I hope you can. Let me know afterwards, Julie, if you can hear it, okay? Now, I see that my computer, let me try that one more time. I'm going to try this one more time. And the reason why is because it looks like something was frozen up on me. Here it comes. There we go. Now, I'm getting a little bit of feedback, so I'm going to mute my mute here. But so here's the thing: we are not going to be looking. I showed that that clip because I wanted to show the transference of transverse waves being generated by the guitar, by the plucking of the strings, being changed into longitudinal waves and the sound waves. But I'm going to focus today on transverse waves because we don't have a lot of time today, and so I want to dive a little deeper into transverse waves. By the way, I think during that part of the video, something happened that happens somewhat regularly here. I mentioned how it's kind of cool living here in Port Huron beside the lake. It also sometimes is not so cool because my internet is really slow, and it tends to drop usually in an hour presentation 4 or 5 times. So if that happens, I'll throw down. I'm keeping an eye on a second computer to see when I get a drop, and we'll see if we can work our way through that. So let's take a look at transverse waves. Now, in experienced physics and in probably a lot of science classrooms that you might be involved in, there's a specific methodology that teachers use. Now, if you're a student sitting there and maybe hearing this for the first time, those lessons that your teachers put together don't just happen, but they go to college to learn about how to teach. And one of the things that they learn is a good methodology for teaching. And it involves, in this case, usually in science, one of the methods we use is what we call the 5 E's: engage, explore, explain, elaborate, and evaluate, which means when I walk into a classroom, I want to have something to catch the students' attention. I want to have something for them to do as a hands-on exploration to get them learning about the content. I then want them to see if they can explain what it is that they're seeing, push them deeper with it when we elaborate, and then evaluate what they've learned. So again, don't think that those lessons just come together for teachers. They put a lot of thought and planning in them. This program uses the 5 E's, and so I'm going to try to roughly follow it today as we go through and get started. So to engage, I want to look at this video and ask if you've ever done something like this before. It's a rock in a puddle video, and let me see if it's going to play. It's not going to play for me. Let me go over to QuickTime. I'm going to pull up the correct window here. Whoops. And I need the rock in the puddle. Here we go. And I'm going to play the video for you, rock in the puddle. Now, how many have done something like this before? You can write in the chat box, throwing a rock into a puddle. Let me ask you something. How can you change the wave that you're creating whenever you throw that rock into the water. Any thoughts on that? Go ahead and type something in the chat box. Julie, let me know what they've got to say.
All right, we have some answers coming in. Amount of force, bigger or smaller rock, how hard you throw the rock, angle, change your angle. You can curve your wrist.
Okay.
Depth of water.
So clearly you have some people who've done this before, and the reason I wanted to put that up there, having an issue with, somebody's having, okay, I'm going to close that. So here's the thing. I wanted to do that little, whoops, let me go back here to my PowerPoint. I wanted to give it a little rock in the puddle just to try it out and see how it worked out. Now, so that engagement is to give you something that you're probably familiar with, which is by the sounds of things most of you are. And now what we're going to do is we're going to take a look at a lab. Now, the lab program for this, for Experience Physics has not been completed yet. But we do have a great partner, Flynn Scientific, and they're actually going to be producing, you see how I've said here, some lab on waves, because these waves haven't been created yet. They're coming soon. But there are actually going to be 4 different versions of the lab, an open, a guided, a shortened, and an advanced. So the open version is the one that's kind of the default version where you'll do a lot of the decisions on how you're going to design the experiment. The teacher will give you usually some kind of an objective, and you'll decide how you're going to do it. The guided has more help for you to help you along with that. Shortened is for that day when you need to get this done in 20 minutes, and then the advanced is when if the teacher wants to give you more challenge. So hopefully they'll be giving you the advanced versions of these. Now, as I said, these are not created yet, but you know, this ain't my first rodeo. And I taught for 25 years, and so I kind of know the type of lab that they're going to suggest on here. And so what I did was I got a microphone stand and a clip for my iPad, and I got my iPad, and then I gathered up some rope and slinky and tape and things like that, and I decided to set up my own physics lab on the dining room floor. Now, my wife was, you know, not too disturbed about that. She kind of played along with that pretty well. So what I did was I laid out on my dining room floor some tape, and I put pieces of black tape that were 5 centimeters apart on one plane. I put red tape on the other 5 centimeters apart. I put a little ribbon tied to the rope over here, and then I thought what I would do is see if I could generate some waves and capture it. Now, here's the thing. You're probably sitting at home now, and maybe, you know, you're bored, and maybe you'd like to see if you could go a little further with learning about physics on your own. Everything that I've used here is pretty simple stuff. It's things that I found around the house, you know, a piece of rope. I've got my iPad. Now, if you've got an iPad or an iPhone, you can use those. And it's just a matter of finding a way to suspend it over the area that you can set up and run your system. Now, I'm going to go to video number 4 now. And so I'm going to go back over to QuickTime. And let me just get my cursor back here and go over to video number 4, which is my rope lab. So here's what I did within the rope lab. First of all, I wanted to see if I could generate a pulse and capture it. And so therefore, I set it up and I can give my rope a flick and I can do that. Now, if I take that video and stop it, I could measure different parts of the wave. I wanted to see if I could make oscillations with this. So I just started the wave and kept oscillating it back and forth. Now, this is tougher than it looks because it's hard to keep a consistent pressure on that. So then I thought, what if I put my video camera or my iPad in slow motion mode and taped it? And so I set on slow motion. You notice I laid my iPhone in there with the timer going. So if I wanted to actually collect data on this, the amount of time it took for the wave to pass by, that sort of thing, I could time it as well. So again, remember my second objective was to give you some tools or suggestions for ways that you can learn about physics and learn about waves. This is one, to look around the house and decide what kind of tools you have that might be useful for you to use. Now, here's another thing I did. I decided to go and try a slinky instead. And so with a slinky, I can generate these transverse waves as well. And in some ways, it's a little easier to control and a little easier to do them than with a piece of rope. And also with the slinky, I was able to generate a longitudinal wave just to see if I could do it. And again, the reason I set up this lab was to show you ways that you can use your own tools to create a lab and collect and gather data on your own. Now I'm going to get away from that. Hang on, let me scrub through this a little bit. I want to show you my, get through to right up here. Here's my longitudinal wave, and I pulled it back and let the wave go. And again, this is in slow motion. You can see how slowly the clock is moving down there, and bam, and there goes my longitudinal wave through it, okay? So I wanted to give you some suggestions for how you could do some waves. Now, it's really important to model waves as well. And suppose that, you know, we're beyond social distancing and so on, and you had a group of friends together, and you wanted to try to find a way to model a wave. Could you come up with an idea for how you could model? Now, a transverse wave, we've got to have the particles moving in one direction while the wave moves perpendicular to that. Well, it just so happens that that there was a wave model that was created in Oakland, California, a number of years ago, and a number of institutions have been striving to perfect this ever since. And so let me get back to where I can open up my window, and I'm going to go to my model of the transverse wave video. And here's our model. Now, Rutgers University is working on the model, and you can see here that the wave is moving in one direction, the particles are moving perpendicular, and there we go. Now, the University of Wisconsin, not to be outdone by Rutgers, has taken this a step further, because not only have they been able to model the wave, and again, you can see the wave going around here, but they're also able to model what happens when the wave hits a surface and reflects back. And so they've taken it even a step further. So again, if you're looking at ways to further your studies in physics, there's an excellent opportunity for you to go to one of these fine institutions and to take part in wave modeling yourself. So let me come back to my presentation. Now, so here's the thing. I set up my lab in the dining room upstairs, and I marked out the floor, and I used rope. I actually used a couple of different sizes of rope. I used a thin rope and a thick rope. I used the slinky, and I was able to capture some data from it. And of course, by maneuvering it around, moving the camera further away, I might have been able to catch more of a wave and do some calculations on it, okay? But I wasn't 100% satisfied. And so what I actually did was I went to the Flynn website and I looked around. Now, Flynn website, let me just pop over and show you, looks like, hang on, get my cursor back, there we go, looks like this. And when you first go into it, you'll see that there's all sorts of stuff in here. And they also have some new at-home, let me go back to Flynn Scientific, some at-home science. And if I click the Explore Now button, uh-oh, my internet is down. Hold on. And please bear with me. I can see right now that my internet is down. And I think I'm coming back. Here we are, the no internet sign. You can see that. Here we are, the internet's back. So, Flynn At-Home Science. They've actually created a website that has resources for you. Here we go. I'm going to load that one more time. And it has resources for you for at home. So I'm going to explore now. And if you start scrolling down, you'll see they have digital learning solutions, at-home live lab series, at-home activities, at-home kits. And if I pop into the at-home activities and scroll down, you'll see that I've got chemistry activities. Oh, look at here. They've got pop, they've got licorice, they've got ice cream, popcorn, all kinds of yummy things that you can work with. Here are some biology with, what do they got? Grapes and a little virus going here. And environmental science and earth science. And then finally down to physics. And oh, look at this. Gummy bears. Now, you're probably wondering how the delicious came into the this presentation. that's where the gummy bears get involved. Because what I did was I went into the website, I discovered this lab on gummy bears, and I downloaded it. And I think you're going to find in the chat that Brian was going to put a link to this website there. Now, if the link is not there, you can just go into Flynn Scientific, do a Google search on it, and go in and you can find that yourself, and you saw where to find it. So let me take a look at this. Now, instead of using my video camera and those types of things, it's suggesting that I use things like C-clamps and duct tape. Well, I have duct tape, gummy bears, and I didn't have any gummy bears at first. Support rods, support stands. I don't have all that stuff at home, but I can improvise. And so what I did was I looked at the materials that were supposed to be used here, and then I looked around my house, and I found, I had some duct tape. And my wife managed to find some skewers for me and said, yeah, you can use those, but if we go to have shish kebabs later, they're going to be a little bit worn and dirty, and that's okay. And I managed to find some old Play-Doh that, we have around for the grandkids, and so I was able to build one of these. And this was my early prototype that I was anxious to try it. I pulled out the duct tape. I taped it between two chairs in the kitchen. I laid the skewers across the duct tape and then stuck a little bit of Play-Doh on the ends of each one. I roughly estimated the size of the Play-Doh. I didn't measure them at all. I roughly estimated how far apart they should be and so on. So I kind of, was trying to see if I could get this to work. And then after being successful with that prototype, I thought, you know what, I might as well do the real thing. So I went to Amazon and I looked up Haribo Gold Bears. And by the way, if you're having a boring day and you want to have a chuckle, go to Amazon and search for Haribo Gold Bears and read the reviews on them. It makes for great reading. I think I spent about a half hour reading through them. But anyway, I went in and I ordered a 5-pound bag of Haribo Golden Bears. Now, I swear to God, as God is my witness, I had no idea how big a 5-pound bag of gummy bears would be, but it's 5 pounds worth of gummy bears, and it's a lot. Needless to say, I'll be eating gummy bears for the next 6 months or more. But anyway, I got some gummy bears. And I went back to my skewers and my duct tape, but this time I was going to put gummy bears in, and the gummy bears are basically all the same size. Now, I quickly learned that skewers are sharp on one end and they're dull on the other end, and gummy bears, when they're being impaled, prefer to have the sharp end. And so therefore, I got my pencil sharpener out and I sharpened the opposite end. So now I could go in and put gummy bears on both ends of my skewers. Now, it took a little while for me to put together some of these, but I eventually ended up with about 36 or so of them. And if it looks like I'm a little OCD, yes, I am. But there was a reason for my madness here. I put red on the one end of each of them, and then I put a different color on the opposite end so I could look for any patterns while I was playing with my gummy machine. Now, then I made up a little device so I could measure the center of each stick as I went down, just to make sure I had them balanced. And then I had to have a place to set up my machine. So down in my office downstairs, I found a piece of aluminum extrusion in my garage. Now, I bought this for a project years ago and have never completed the project, so I thought I could use that. A board would do just as well. Or as a matter of fact, a couple of chairs, as I did with my prototype, would work just as well too. Then down in my basement, I set up a little lab. So I got 2 stools, I got a couple of boxes, I set up the extrusion between the boxes, and I set up a little grid in the back using sticky notes. And then I built some little bookends on this that I could then clamp to the ends of the metal bar and make something that looked like this. So the next step was to take my duct tape, double over the end, clamp it on, run it the length of the extrusion, and double the other end of the duct tape together and clamp it on, make sure they were pulled nice and tight, and then to place all of my gummy bear skewers on the duct tape. And I made a little jig that was 5 centimeters across, and made sure I placed them all approximately 5 centimeters apart as I went for consistency, okay? So it ended up looking something like this, And here's a video of what it looks like as I kind of ran down the edge here. So this was a pretty cool thing to make, and I would encourage you, if you like gummy bears, good excuse to buy a 5-pound bag of them, and it will give you a medium that you'll find probably more useful than trying to whip a rope around your dining room. And so what I did was I put together some experimentation on the Gummy Bear Wave machine. And so I got my wife to sit at the far end here and generate waves for me while I recorded it. And again, because I wanted to have the possibility of measuring the time that it took for a wave to run down through the wave generator, I put my, you can notice that I have my iPhone sitting there with the timer running on it. So let me go up and go back again to my videos. Let me open up my window and go to the, oh, I don't have my Gummy open. Hang on one second here. Let me go over to my, let me see, let me go over to my here, Gummy Bear Wave machine, and here it is right here. Now, I started off, I said to my wife, I'd like you to put down 1 centimeter displacement, if you would. And so here's what she did. She was generating waves through the gummy bears. And it's the Gummy Bear Wave machine, and here we go. So she displaced it about 1 centimeter and let it go, and you can see how the wave ripples back and forth, okay? And then I said, well, let's try a 2 centimeter displacement and see what happens. And so she gave us 2 centimeters of displacement back and forth. And you can see that the up and down motion is quite a bit larger, although it doesn't look like the wave's moving very much faster. Now we're trying with 3 centimeters. And again, you'll notice that the speed of the wave is very similar, but the displacement of the gummy bears is a little different each time. And then I asked her if she could make some oscillations with the gummy bear, and she was able to do that and create some nice standing waves. Whoops, I guess I cut that one a little too short. I also wanted to see if I could freeze the frame and make measurements with it, and yes, in fact, I could freeze the frame. And the final thing I wanted to do was get some slow motion going there. And so again, I put my iPad on slow motion and had her start generating a wave so that I could stop the wave and watch it happening in slow motion. So again, we don't have time to take measurements today of the various parts of the wave that are found here, but here's a great way for you to develop something that you could use at home. Again, improvise, find what you've got at home that's going to work for you, and then you could set up and take some of your own measurements. Now, let me go back to my PowerPoint. Whoops. There we go. So here's a challenge for you to take with you. Okay, number one is to go to flintsci.com, Flynn Scientific, download the Gummy Bear Wave machine, and build your own wave generator. So there's a little assignment that you can do. And I think there's a link in the notes that takes you there, and it'll also be found in the blog at the end, okay? So what can we find out about waves by using the wave generator or by putting ropes on the floor? The first thing is that, again, when the end of the wave is oscillated up and down, the energy is transmitted through the rope, and it's visible as an up and down motion throughout, okay? And the thing is, we already looked at this, how in a transverse wave, the particle movement goes in one dimension while the wave movement goes in another. Well, what are some of the things that we can measure in this wave? Well, first of all, the upper part of the wave we call the crest. The lower part is called the trough. Again, probably from middle school, you're familiar with these terms. The displacement of the particle from its rest position, either in the upward position or in the downward position, is known as the amplitude. The distance from one crest to another, or from one trough to another, is the wavelength. And that's measured, we use the symbol lambda for wavelength, and it's measured usually in meters or fractions of meters. For measuring transverse waves, one of the things that we can measure is the frequency of the wave. Now, the frequency is the number of waves that pass a given point in 1 second. Now, if you had your wave bear generator set up, what you'd have to do is identify a point that you wanted to see how many waves pass that point per second, and you'd need a stopwatch. And you'd start your waves generating, and you'd have to count the number of waves that pass by in a given time, and then do a little bit of math on that to solve for the frequency, okay? Frequency is measured in hertz, and that's in cycles per second. So let me give you a little problem here and show you how that works. So first of all, suppose I was out on Lake Huron, and I was looking at a buoy out there that has 10 wave crests pass it in 20 seconds. How could I calculate the frequency? Well, the frequency would be the number of crests, or the number of cycles that pass by, divided by the time in seconds. And so if I fill in those values, I've got 10 cycles in 20 seconds, which gives me 0.5 cycles per second, or 0.5 hertz, okay? A second thing that we can measure with a wave is the period of the wave. And the period is the time it takes for one wave to pass a given point. So in other words, if we look at one wavelength, the period would be the time it takes for this wave to pass from one crest to the next. And again, we'd need to time it, and it would probably be pretty hard to time one wave crest, although if it's a large water wave, that might be one thing, whereas smaller waves in the gummy bears might be harder. So you could count up a number of them. Now let me go back to that, and the time for the measurement for that is seconds. So let me go back to that same question. Out on Lake Huron, a boy has 10 wave crests pass it in 20 seconds again. Calculate that, and this one should say the period. I made a mistake there. So the period would be the time in seconds divided by the number of cycles, just the opposite of what we saw before. So 20 seconds divided by 10 cycles means it's going to be 2.0 seconds. Now, the frequency was 0.5 seconds. The period is 2.0 seconds. Sorry, 0.5 cycles per second, hertz, 2.0 seconds. In fact, the frequency and the period are reciprocals of each other. The frequency is 1 divided by the period, and the period is 1 divided by the frequency. Now, if we were going to calculate the speed of a wave, and someone was asking about the size of waves and the speed of the waves that were causing the destruction, if we were going to calculate the speed of waves, we'd have, if we were looking at a particle moving, we'd look at the velocity as being the distance divided by the time. Well, if we're looking at a wave, we also need to have some aspect of distance and some aspect of time. And in this case, the velocity is equal to the wavelength divided by the period of the wave. Now, taking that formula, wavelength divided by the period, remember the period is the inverse of the frequency. So the velocity equals the wavelength divided by 1 over the frequency, and canceling out and working through the math, then the velocity equals the frequency times the wavelength. So velocity equals lambda divided by t, the period, or velocity equals the frequency times the wavelength. Now, it's possible to display waves using graphs. And I want to show you 3 different types of graphs that can be used to determine waves. Number 1 is a distance graph. Now, with a distance graph, what you're doing is taking a snapshot of the wave at one instant in time. And it's looking at the amplitude and the wavelength. And if we look at the distance, we're seeing how the particle moves as far as the distance between successive points and the crests of a wave, okay? So we can do a distance graph in order to determine some aspect of a wave's properties. Now, we could also take one particle from that and measure it as it moves up and down through its cycle and graph that movement with regards to time and create a time graph. It's showing the up and down motion of one part of the medium. The period t is the time it takes for the particle to move through one full cycle, and the frequency is the inverse of the period, f equals 1 divided by the t. The final way is a wave graph, and here we're looking at the wave speed, which is how far the wave moves in a unit of time. In other words, we're looking at the ratio of the wavelength, the period, and the wave speed. Now, another partner we have with our new program is PhET. PhET Simulations are created by the University of Colorado. And I'm going to take a quick look at two of these, and I'm going to send you links to where you can go in and look at them. But the thing is that it's difficult sometimes when you're creating your own devices for measuring speed, wavelength, distance, period, and so on. It may be a little more difficult than using a simulation. So let me take you and show you two simulations. Now, this first one is an introduction to waves. And I'm going to just pop over to here, and I'm going to go to my introduction of waves right here. Now, you'll see that I can work with water, I can work with sound, I can work with light. Of course, I'm going to go in and work with water. Now, here's the thing. I can start this thing going, and I can create a constant wave, or I can create a pulse. So the constant wave looks like this. And if I went with a pulse, it would look more like a single wave. Now, right now, I'm looking at the top view as if I was looking down at some kind of a ripple tank, but I want to take a look over at the side view here. And so what I'm going to do is set up a wave in here and click on it, and I can now watch the wave moving up and down. Now, notice I have controls over here for amplitude and for frequency. And so if I set this up and start this going, continue moving with this, I can increase the amplitude and see what effect it has on the wave. Or I could decrease the amplitude and see what effect that has on the wave. Now, could I measure things on this wave? Well, let me go up to a maximum amplitude again. Let me also take a look at the frequency. If I change the frequency of the wave, you notice that the waves occur more rapidly, okay? Do they move faster across the screen? If I slow down the frequency, you can see that they're not generated quite as quickly. Do they move faster across the screen? Well, I'm going to leave you with that question, but let me show you that you can take a measuring stick, I can take a wave, pause it, and I can pull this measuring tape in, place it at the top of one wave, measure over the other wave, and find the length, all right? Now, I can also find the time by timing a wave, and when I start that up, I can measure the amount of time it takes for one wave, two waves, three waves. In other words, I can generate my own data that I can then go back and collect. Now, the last thing I want to show you is this thing that will graph the waves. And so if I take this over and place it over here, let's say, let me get rid of this one, put this one on the wave and start the wave one more time, what it's going to do is it's going to graph the wave for me, and I can pull data from that too. So there's one of the PhET simulations that you can use to learn about waves. Now, a second simulation is called the wave on a string. And wave on a string, when you first open it, it has it set up with a monkey wrench, a clamp with what simulates a rope with a string of beads with about every 10th bead is a different color so that you can look for patterns within the bead. Now, I can do this manually. So in other words, I can generate a wave manually by flicking it up and down, okay? And I can watch and see what happens, how the wave bounces back. Remember my students at Wisconsin, when they bounce back, when their wave bounced back rather partway through. So I can go in and have a look and see how that bounced back. Now, what if I had a loose end on this? Well, I can do that same wave and see what happens if the end is loose. Or what if there's no end on this? I can generate a wave, generate a pulse in here and have it go down and flow through. Now, I can also do a pulse. And by hitting that pulse, it allows me to look a little more closely at it. So there's one with a loose end, or with a no end. There's one with a loose end. Here's one with a fixed end. And I can start to study how waves interact with depending on how the wave is held. Now, one of the things that I found that was most difficult in using the rope was that I had the rope attached to something, and it was really hard to keep a constant pressure on as I was making the waves in there. Now, this is here's one of the cooler ones. I can also have the waves oscillate back and forth, and I can have the wave oscillate as a fixed end. I can have it oscillate as a loose end, or I can have it oscillate with no end in sight at all. Okay. Now down below, again, I've got some control over the amplitude, so I can increase the amplitude of the wave. I can increase or decrease the frequency of the wave. And what I'm wondering is what effect that might have on the speed of the wave. Well, what I can do once again is I can, let me slow this down first of all, slow motion, and let me try to freeze this wave. You know, let me reduce the frequency a little bit here. Or sorry, let me increase the frequency, I mean. And I want to try to freeze this with 2 waves. Oh, okay, hold on. My damping. Now here's the other thing about damping. Damping is like friction on the wave, and you'll notice the wave gets a little smaller as I go along. If I drop down the damping or remove the damping, now I don't lose anything from my wave because of friction. So let me stop that. Now I've got 2 successive waves. I can go in here and I can pull up a series of tools. So for example, I could pull up a ruler. I could measure the wavelength of the wave here. I could also pull this in and measure the amplitude of the wave. I've got a timer that I can build in so I can find the time for the wave being generated. I can also pull up a reference line that I could set to determine either the maximum or height of the wave or the minimum depth of the wave. I can pull up a timer so I can do timing. And again, when I go in slow motion, it times in slow motion as well when I start my timer, so I can collect data. So I just wanted to show you those methods for collecting data using some of the partners that we have with the new program. And again, you can go in and experiment and play around with these all you'd like. We've got links to them in the thing. So challenge number 2, try the PhET simulations, and you can just go in and Google PhET, P-H-E-T simulations, and it'll take you to them. There are a whole number of them, or you can click the links in the blog and go to specific ones. So, spoiler alert. Once you play around with these, there are a couple of things that you're going to notice. Wave speed is really constant for a medium, okay? So in water, the wave speed is basically constant depending on the nature of the water, okay? The amplitude, though, depends on the energy that you put into the wave. So the more energy you put in, the higher the amplitude is going to be. So think about the rope. If I just give a little shake on the rope, it's going to produce a small wave. If I put a big shake on the wave, it's going to create a big wave as far as the amplitude is concerned. But what about the speed of the wave? The speed of the wave should remain the same for both. Now, the evaluation part, question like this, for example. At the beach, you time the wave crest hitting the shore and determine there are 20 seconds between crests. Determine the frequency of the wave. Now, that one you could do now using the calculations that we looked at. And by the way, I got through maybe a quarter of a lesson here going through this, a quarter of the lesson that we're looking at, okay? The second question you wouldn't be able to answer at this point, would you expect the frequency to change if you made your measurement further out from shore? Because what happens further in the lesson is it takes a look at what happens when the water gets shallower. And as a matter of fact, that does affect the frequency of the waves. Now, back to the phenomenon. So let's see if we can pull this all together. Now, we had a lot of really good questions there, and let's see if we can answer some of those questions now. Now, normally what we would have you do is take a form that looks like this. It's a claim evidence reasoning. We'd have you make a claim. Why do you think we have so much erosion on the Great Lakes right now? What's causing it? And have you make a claim for that, cite the evidence you have for it, and then explain the scientific reasoning behind it as well. Now, we don't have time for that today. We're getting down close to the end, so let me move along and let me give you a little spoiler alert. As of April 10th, 2020, Lake Superior was 14 inches above its April average. Lake Michigan and Lake Huron, they're essentially one lake where they come together up around the Straits of Mackinac. It's such a large opening that there's really not much, there's no difference in the height of the lakes. They were 36 inches above the average. Lake Erie, 33 inches above the average, and Lake Ontario, 16 inches above the average for April. Now, here's the data on Lake Huron and Lake Michigan. In other words, the two lakes basically the same height. Now, here's the data from this. The record highs is this aqua line along the top. And so you can see that is, it's somewhere around 581 point something. Now, that's feet above sea level, okay? Now, the record lows are shown as this brown line down at the bottom. And the month's mean, in other words, for all the recorded data in history, the mean was this green line. So you'll notice that typically water levels are low in the spring and fall and the winter, and they tend to be higher in the summer, okay? Well, let's look at 2019. These were the daily levels for 2019. You'll notice that they are lower than the record high levels. However, they are quite a bit higher than the record low, than the average, and definitely much higher than the record lows. And if we look at 2020 so far, look at where we are. So far, every month, the high water mark has been above record highs. So in other words, we're setting records in the Great Lakes the whole way. So what does this have to do with the price of tea in China? Well, first of all, the Great Lakes water levels have swung from record lows to record highs, and here's why. Now, when I first moved to Michigan, I bought an old sailboat, and we were worried for a number of years because we was getting to the point where there were some harbors that we could barely get into. We would run aground. In fact, the first day I had my boat going out of Metro Beach in Detroit, I ran the boat aground because the water was so shallow, and had to work like crazy to get it off. But anyway, they've gone from record lows to record highs, and here's why. Well, it's what used to be public enemy number one, climate change. And of course, a few months ago, it got bumped off the public enemy number one list by COVID-19, and that's going to be my only reference to COVID-19 today. But climate change has started to be pushed to the back, but it's still a really important factor. And here's why. Climate change can affect extreme weather. There's still a lot more to learn. And we do have things like, football field size section of a popular bike trail collapses into Lake Michigan because of this climate change. So first of all, what causes water waves? Somebody had a question about why we have the waves. Why are there such big waves? What causes waves in the first place? Well, the answer is wind. And the wind-driven waves, or surface waves, are created by friction between the wind and the surface water. If anybody ever happens to be going through the Port Huron area, southern tip of Lake Michigan or Lake Huron, when you go down the St. Clair River on a windy day when the winds come from the south, there's a 4-knot current going down the river, and when you get winds of about 12 to 15 knots going north, the friction that's there creates these big, huge 5 to 6 foot waves, standing waves in the river. The kite surfers absolutely love it, boaters not so much. So as the wind blows across the surface of the ocean or lake, the continual disturbance creates a wave crest, and that's what gets waves started in the first place. Now, what determines the size of the water waves? Why are these water waves going to be so big? Well, the strength of the wind determines the water waves. That's one of the things, okay? The stronger the winds are, the higher the waves are going to be. The second, the duration that the wind blows. So if I look at a weather map and I look at the winds or what the winds are going to be over the next day or so, I can see whether the waves are going to be getting bigger or whether they're going to be smaller, depending on how long they've been in a specific direction. And the third thing is the distance over which the wind blows across open water. And we call that the fetch, okay? Now, you've seen weather maps, and you may be familiar with high-pressure systems and low-pressure systems. Now, in the Northern Hemisphere, high-pressure systems mean there's a lot of air packed in. And that air is going to be drawn outwards to low-pressure areas. And in the Northern Hemisphere, it circulates in a clockwise direction, okay? Now, in a low-pressure area, there's not much air in there, not many air molecules, and so hence lower pressure. And the air molecules get sucked into the middle, into the low-pressure system, and they go in a counterclockwise direction in the Northern Hemisphere. And you may recognize that as being the Coriolis effect, okay? Well, let's overlay that on a map of Michigan. So I've got high-pressure systems, low-pressure systems, and depending on where those systems are located, we will have winds that are moving one direction or another direction. And if you look at the map, if I clear that out, you'll notice that when winds are blowing from the north or northwest on Lake Michigan, they're going to have a lot of fetch, and the stronger the winds are, the bigger the waves are going to be. Over on Lake Huron side, when there's a low pressure system to the east, then you're going to find waves blowing from the northeast. And again, over that fetch of distance, about 200 miles or so, 250 miles, it's going to create very large waves. Now, somebody asked how big the largest waves are. Back when Hurricane Sandy hit New York, we had waves in Lake Huron. We had 35-mile-an-hour winds for 3 days straight. And down where I live, down near the southern tip, we had 11-foot waves that were washing in. Now, those weren't hitting the shore. They were slowed down and dropped down by the time they hit the shore. But out on open water, there were 11-foot waves. You may have heard of the Edmund Fitzgerald, made famous in a song by Gordon Lightfoot. The Edmund Fitzgerald was a freighter that was sunk back in the 70s on Lake Superior. And they found the wreck, and they think that the wreck actually, a couple of possibilities, that it was broken in two by a wave or was submerged by a wave. It hit the wave and sunk and kept going straight down. And the waves they think that hit the Edmund Fitzgerald were somewhere in approximately 30 feet high. Now, Lake Superior is 300 miles from one end to the other. When you look at fetch, that's a lot of fetch, a lot of distance for that those water waves to move over and to accumulate waves. So here's the litany. Here's how climate change affects it. More storms in the Great Lake Basin means that you're going to get higher water levels in the Great Lakes. A friend of mine sent me a video that I wanted to put in here. I didn't get a chance to do it. He was down in Put-in Bay on Lake Erie, and the water level is up over the roads. The houses are being flooded out and so on. And those high water levels are a result of more water getting into the lakes because of more storms. The water levels top wave protections. If you go up and down the lake here, you'll see people have built breakwaters. They've built piers going out to trap sand and so on to protect their shoreline so it doesn't go down. And if you look up some more videos online of the Great Lakes, you'll see people are building like crazy to build walls to stop. But when the water level goes up, it tops those wave protections. It goes over top of those. More intense storms are going to mean stronger winds. And of course, the combination of the stronger winds are going to generate larger waves. And the larger waves, of course, are going to go over top of those storm protections, wave protections, cause more erosion and more destruction. And so that leads us to the solution to the problem, which is climate change. Maybe it's public enemy number two right now, but still keep it on the public enemy list and see what we can do about it. So thank you very much for your time. I can sit here and answer some questions. I'm not sure if everybody else has to get going, but thank you for being here today, and I will pause now and just take any questions that anybody might have.
All right. Thank you so much, Chuck. If anybody still in the presentation would like to ask any questions, please go right ahead. If not, you will be getting a survey when you log out of this. You also get a sort of a bounce back auto email that has my email address in it, and feel free to respond to that. All of the links are in the chat box as well as the blog link, but if you're having trouble locating them, either shoot me a question, ask the question here, or respond to the email. Thank you all so much. Looks like a couple people are hopping off. It is the top of an hour, but we really do appreciate your time today. Thank you for joining us.
Thank you.
Oh, we have a question for you, Chuck. How long do you think it would take to cover this lesson in the classroom?
The lesson itself, from looking at the teacher's edition, the lesson would take probably about 4 class periods. And the reason I say that is because there will be a video that is to engage the students at the beginning. There will be the lab that they're doing, and again, that lab may last anywhere from 20 minutes if you choose the shortened version of the lab, to an hour or thereabouts with the more complex or with the more challenging versions of the lab. Then you've got the PhET simulation is suggested as one of the places for students to go to do some experimentation with and do some measurements, so they can go and do that. So it would take approximately, I think they have the timeline set up for about 4 days, 4 40-minute periods. The part that I did would probably be a day or two.
All right. Does anybody else have questions in the group? We got a few thank yous.
Okay. Well, you're very welcome.
All right. Okay, well, thank you all so much, and I hope you have a wonderful day.
Okay. Thank you. Bye-bye.
Bye.